Hello learners, welcome to this course on embedded system design using PIC16F877 microcontroller. In this tutorial, I will be discussing about on how to interface a temperature sensor with PIC16F877 microcontroller. So a temperature sensor, we are going to use LM35 as a temperature sensor and we'll be connecting it with the PIC16F877 microcontroller. Then we try to do the monitoring of the temperature. So the applications are we can have or we can build a temperature based home automation, industrial process automation, etc. So we have different types of ADCs available, 8-bit, 10-bit, 12-bit, N-bit ADC. So ADC is nothing but analog to digital converter. So where this 8-bit, 10-bit, 12-bit represents the number of bit output from a ADC. So for example, in case of a 16F877 microcontroller, we have a 10-bit ADC inside. So after the conversion process, the PIC16F877 microcontroller will produce a 10-bit result. So this 10-bit result can be read by the microcontroller from the ADC and it can be used for displaying or for control operations. So the type of ADC which is available in our PIC microcontroller is successive approximation ADC. So here I have shown the block diagram representation of a successive approximation ADC where we connect the input sensor value to the sample and hold circuit. So here the sampling or the samples of the analog signal will be selected and this signals will be given as an input to your comparator. And we have SAR register, successive approximation register, which gives for a particular voltage what will be its corresponding digital bit pattern. So here I have showed it as a 8-bit SAR register. If it is a 10-bit SAR register, the number of bits coming out of this SAR register will be D0 to D9, which will be a 10-bit value. So for each voltage, the corresponding binary values will be saved in the SAR register. Then once the comparator gives an output, the corresponding binary bit pattern will be obtained through the SAR register and it will be given as an output D0 to D7. So in order to get the D0 to D7, the value in the SAR register will be converted to an analog voltage using a DAC. DAC is a digital to analog converter. So this voltage coming from the value pointed by a SAR register will be compared with the input voltage. If both matches, then the corresponding binary bit pattern is the bit pattern for the input signal. For example, let us take, we have an input voltage of 2.5 volt. So first what will happen, the first entry in the SAR register will be compared. So for example, 0 volt, I will get all zeros in the output. So this all zeros will be converted into an analog value which is nothing but a 0 volt here. So now 2.5 volt is compared with the 0 volt. So the comparator will not produce an output. So thereby the change of value in the SAR register will take place. So it goes to the next higher resolution value. Then again it gets converted. It produces a voltage. So when there is a match here, the input voltage is 2.5 volt and this point negative terminal of the comparator also gets a 2.5 volt. Then the comparator is given output signal. So this output signal will be used for identifying the bit pattern because for that voltage we know the bit pattern. So then that bit pattern will be obtained as a digital data for your analog input. So that is how the successive approximation ADC is going to work. So in order for this ADC to work, we can provide a reference voltage. We need to provide a reference voltage. So this reference voltage can be a IC voltage or we can use external reference voltage or internally generated voltage can also be used. So when we talk about an ADC, so ADC important thing is we need to know about the resolution of an ADC. So resolution is nothing but the smallest voltage change which can be represented as a proper digital output pattern. So what value of voltage can be represented in a proper binary bit pattern? So that is nothing but the resolution. So for example, it can be computed using this formula, resolution equal to V reference divided by 2 power n minus 1, where this n stands for the number of bits of your ADC, whether it is a 8-bit ADC, 10-bit ADC or 12-bit ADC, that represents the n bit. So in our case, PIC16F877 microcontroller as a 10-bit ADC, so n value will be 10. So if I take a reference voltage of 5 volt, so which is nothing but 5000 millivolt, divided by 2 power 10 minus 1, which gives about to be 4.88 millivolt. So this is the smallest voltage change which can be represented by a ADC output. If my sensor gives a value less than this 4.88 millivolt, in that case, we need to either go with a 0 volt approximation or 4.88 millivolt approximation. So proper binary bit pattern will not be obtained. So the minimum resolution for a 10-bit ADC with a reference voltage of 5 volt will be 4.88 millivolt. If I want to increase the resolution, even smaller voltages we need to measure properly. In that case, what I can do is we can change the reference voltage. So by modifying the reference voltage, the resolution of your ADC is improved. Here you can see, if I use a reference voltage of 2.5 volt, which is nothing but 2500 millivolt divided by 2 power 10 minus 1, you can see the resolution is about 2.44 millivolt. So now the smallest change which can be represented is 2.44 millivolt. Same way, if the number of bits of a ADC changes also, the resolution will get modified. Here you can see, if the n takes a value of 8, in that case, for the reference voltage of 5 volt, we will get a resolution of about 19.6 millivolt. So here you can see, I have shown a table. Okay, so for a resolution of 4.88 millivolt, if I take a reference voltage of 5 volt and let us consider a 10-bit ADC, in that case, the 0 volt input will be represented as 10 zeros. The next voltage level which can be converted into a proper binary bit pattern is 4.88 millivolt. So for 4.88 millivolt, you see 9 zeros and 1. And again, adding another 4.88 millivolt, it will be 9.76 millivolt. So the next voltage which can be properly measured is 9.76 millivolt. So this 9.76 millivolt will result in 8 zeros, 1 0. So like that, if I go, if my input voltage reaches 5000 millivolt, in that case, I will get 10 ones as an output. So this is the digital data which will be coming out of your ADC when we have this analog input voltages. So in this program, we are going to connect a potentiometer to PIC16F877 microcontroller. So we know that in PIC16F877 microcontroller, we have 8 channels and a 10-bit ADC is available. So I am going to connect this potentiometer to one of the channels. So one of the channel is AN0. So AN0 is available in port A 0 pin. So RA0 or AN0. So I am going to connect a potentiometer to AN0. So this potentiometer represents a sensor. So it can be a temperature sensor, it can be a pressure sensor. So whatever might be, the sensor output will be a voltage or current depending upon the physical quantity. So for simplicity, I am going to connect a potentiometer with PIC16F877 microcontroller to channel 0, which is AN0. And the 10-bit result will be obtained. So the 10-bit result will be visualized through 2 ports, port B and port C. So the LSB data will be available in RB0 and MSB data will be available in RC1. So we can visualize a 10-bit result and we are going to connect an array of LEDs to this 10 port pins. So thereby we visualize a 10-bit result in an LED. So for this program, we are going to use IDE, which is nothing but Micro C Pro for PIC, where we will be writing an embedded C code and converting this embedded C code into a hexadecimal file. Then we will be using a simulator Proteus 8 Professional for building the hardware circuit and then try to put that hexadecimal file onto the microcontroller in a Proteus 8 environment, then check the result. So I am going to use a reference voltage of 5 volt, and we already know that PIC16F877 microcontroller has a 10-bit ADC. So the resolution of your ADC is 4.88 millivolt. So before moving on to the program, let us see the important registers associated with the ADC of your PIC16F877 microcontroller. So one of the register is ADCON 0 register. So ADCON is nothing but ADC control 0 register. So it's a 8-bit register available in your PIC16F877. So here I have given the details. So if you see, the 0th bit is a AD on bit. So AD on bit in the sense whether I want to switch on the A to D converter or not. So here you can see if I put 1, then A to D converter will be operating. It will be in on state. If I put 0, then the A to D converter module will be shut off. So either I can switch on a ADC or I can switch off a ADC. Then the second bit is a go done bit. So go done bit in the sense we can start the conversion process or we can give a signal to the ADC to start the conversion process, that is through go bit. So if it is 1, start of conversion will happen. So ADC will start its conversion process. Once the process is complete, ADC will change this bit from 1 to 0, which is done bit. Done is an active low signal. So once we monitor this done bit, if it has gone to 0, which means the conversion is complete, we can read the result from 2 registers, ADRESL, ADRESH register. Both are 8-bit registers. Because since we have a 10-bit value, so this 10-bit value will be residing in ADRESH and ADRESL registers. So this go done bit, go bit should be given by the programmer and the done will be set by the hardware ADC. So we have to put 1, which means start the conversion process. Once the process is complete, the ADC will intimate us by changing this bit from 1 to 0. Next 3 bits, CHS2 to CHS0. So this is for channel selection. So we know that we have 8 channels available in a PIC16F877 microcontroller. So we can select these channels. So for example, if I put 0, 0, 0, then channel 0 will be selected. 0, 0, 0, channel 0 will be selected. So channel 0 is nothing but AN0, which is available in port A0. 0, 0, 1 means channel 1 will be selected, which is nothing but AN1 channel. 0, 1, 0, AN2. 0, 1, 1, AN3. 1, 0, 0, AN4. Then 1, 0, 1, I have AN5 in port E, 0th pin. 1, 1, 0, AN6. 1, 1, 1, AN7 again in port E, 2nd pin. So this is used for selecting a channel. Which channel will be routed to the ADC? That will be decided by this CHS2 to CHS0. Then we have the MSB part, 2 bits, ADC S1 and ADC S0, which determines the conversion clock speed. So the ADC, which is a 10-bit ADC, it takes about minimum 12 clock cycles to complete the conversion process. So we need to determine at what speed the conversion should take place. So that is decided by these 2 bits, ADC S1 and ADC S0. So if I put a value of 0, 0, then the conversion clock speed will be F oscillator by 2. So F oscillator is nothing but, if I connect a 20 MHz crystal, it is internally divided by 4 in the PIC microcontroller, thereby it becomes 5 MHz. Then this 5 MHz will be divided by 2, which is nothing but 2.5 MHz. So the conversion clock speed will be at 2.5 MHz if I put 0, 0. Same way if I put 0, 1, which is nothing but F oscillator by 8, 1, 0 means F oscillator by 32, and 1, 1 means we can use an internal clock frequency. So these 2 bits are used for selecting the speed of conversion process. Whether I should have the conversion process very quickly or it should be low. So this is one of the control registers. ADCON 0 is one of the control registers. And there is another control register for ADC, which is ADCON 1. ADC control register 1. Again, this is a 8-bit register. So here the lower part, which is PCFG3 to PCFG0, 4 bits. So this decides whether I am going to use the port A or port T pins as a analog pin or a digital pin. And also it will be used for selecting the reference voltage for your ADC. So for example, if I put this PCFG3 to PCFG0 to be 0000, then you can see here from AN7 to AN0, all the 8 channels are configured as analog channels. And what will be the reference voltage? Reference voltage will be, positive voltage will be VDD and negative reference voltage will be VSS. So the IC supply voltage is taken as a reference voltage. So we have 8 channels and there is no external reference voltage. So that is specified by 0. So if I put a value of 0001, in that case, I am going to have the channels to be analog, and we can use RA3 to give an external reference voltage. So external reference voltage can be provided, thereby the resolution of the ADC can be changed. So we can use the RA3 pin to connect the external reference voltage. So thereby I get 7 channels and 1 reference voltage, which is an external reference voltage. So like that we can have a multiple combination. If in our application we don't have any sensors, any analog sensors, in that case I can use this port A and port E as a digital pins. In that case I can use this combination 0, 1, 1, X. X stands for don't care condition. So I can take a value of 0, 1, 1, 0 or 0, 1, 1, 1, which means all the pins are configured as digital pins. So we can connect any digital device to the port A and port E pins. Where I can switch off the ADC because we are not going to use a ADC. So all the pins we can use it as a digital pin. So by putting a proper value onto this PCFG3 to PCFG0, I can select how many channels we require for a particular application. And we have one more bit, MSB bit, which is a ADFM bit, which gives the result, how the result will be saved. So for example, if the ADFM bit is 1, which means the result is write justified. So write justified in the sense I have 2 registers, AD, RE, SH and AD, RE, SL. So 2 registers, 2 8-bit registers are there. So if my ADFM is 1, then the result will be write justified. So write justified in the sense my result will be like this. It will be saved like this. So in the ADRESH, lower 2 bits we will have the result, and ADRESL we will have the complete result. Whereas in case of 0, if ADFM bit is 0, then it will be left justified. Left justified in the sense that now the result will be on the left side. So left side in the sense we make use of ADRESL completely, and ADRESL we use the MSB part, 2 bits. So how a 10-bit result is stored in this 2 8-bit registers. So that is specified by the ADFM bit. If ADFM bit is 1, the result is on the right side, and if it is 0, then the result will be saved on the left side. So this indicates how the result is being stored and how we need to read the result. So here we have discussed about the 2 control registers, ADCON 0 and ADCON 1. We have to make use of this registers in our program. So now let us start with the programming part. of connecting a potentiometer to a PIC16F877 microcontroller, then try to visualize the 10-bit result on an LED. Now let us open Micro C Pro for PIC. First we will start with the circuit part. So I am going to use Proteus 8 Professional. Create a new project. So select a location for a project. LED ADC. So I create a location for storing the project. Give a name for the project. Next, select a default schematic. So I'm going to use a default schematic. We are not going to create any PCB layout. No firmware. Next. So only schematic is selected. Press finish. So here we are going to build the circuit. First we will select the components required for building the circuit. So let me pick the components. So PIC16F877. Select the IC, add it to the list. Then I require a bar graph LED. So let me take a red color, add it to the list. Then I require a potentiometer. So let me select a potentiometer, add it to the list. Then let me select the crystal, capacitors, switch, resistor. So these are some of the components which we require for building the circuit. After selecting the components, press OK. So now let us build the circuit here in the schematic. First let me select the IC, place it onto the circuit. Connect the capacitor and crystal to the circuit. So I am going to rotate it, place it onto the circuit. Connect the crystal to pin number 13 and pin number 14, which is oscillator 1 and oscillator 2 pin of your microcontroller. Then I am going to connect a capacitor to this crystal to produce a stable square wave by the crystal. So I connect two capacitors to the oscillator circuit. Connect the other end of the capacitor to ground. So let me change this capacitor value to 33 picofarad. So right click on the component, edit properties, 33 picofarad. Same way other capacitor too, I am going to change it to 33 picofarad. Crystal, I am going to use a 10 megahertz crystal. So right click on the crystal, edit properties, 10 megahertz. Okay. So next is we need to build the reset circuit. Again go to components mode, select the switch, place it onto the circuit, resistor, place it onto the circuit, connect one end of the resistor with the switch, other end of the resistor I am going to connect it to a supply. So go to terminals mode, select supply, place it onto the circuit, connect it to the resistor, and ground gets connected to the switch. Then the intermediate point I am going to connect it to a memory clear pin. So by default the memory clear pin will be at logic high. Whenever I close the switch, the pin will go to 0, thereby reset operation will be perform. So now let us connect the potentiometer to RA0 pin. So again go to components mode, select the potentiometer, place it onto the circuit, connect it to the RA0 pin. So because we have used AN0 pin, right? AN0 pin. So connect one end of the potentiometer to a supply, other end to a ground. So by varying the potentiometer, I can change the voltage given to the channel of your ADC. So now let us connect the LED part. So let us go to components mode, select the bar graph LED, put it onto the circuit. So I am going to connect it to RB0 will be the LSB part and RC1 will be the MSB part. So let me connect the 10-bit value to the bar graph LED. Ten-bit value is connected to the anodes of your bar graph LED. Cathodes, I need to connect it to the ground. So go to terminals mode, select ground, place it onto the circuit and connect the cathodes to the ground. Okay. So this completes our hardware circuit. So we have connected the oscillator circuit, reset circuit, and we have connected a potentiometer to AN0 pin of your PIC16F877. And in order to visualize the result, we have connected the 10 port pins to the bar graph LED. So let us save this project. Now let us go and build the program for this. Let us go to micro C, create a new project. Next, so let me select a location for saving this project. Select the location. I am going to give a name for the project, LED ADC. So the IC is selected, PIC16F877 microcontroller, and I am going to use an oscillator frequency of 10 MHz. So 4 things we are doing here: selecting a location for storing the project, give a name for the project, select the microcontroller for which we are going to do the program, and select the clock frequency. Press next. We don't have files right now, so leave it as it is, press finish. So this is the location where we are going to do our program. So let us save the project with the name LED_ADC. So let me open the program. So here I have a program. Select the program. Place it onto your window. Now let us try to understand this program. So as I said, I am going to use addcon 1 and I have set it to 80. So 80 means I am setting ADFM bit to be 1 and PCFG3 to PCFG0 I am setting it as 000, which means port A and port E are configured as analog channels. So let me show this. 80 represents so here we are putting 1 0 0 0. This is 8 0 0 0, which means 8. This is 0, 80. ADCON 1, we are putting 80. So ADFM bit 1, in the sense our result is write justified. And here we are putting 0, 0, 0, 0, which means I am configuring all the port A and port E pins, all the channels as a analog channels. And what about the reference voltage? I am going to use the IC supply voltage as a reference voltage for this conversion process. So that is why we specify here as a ADCON 1 equal to 0x80. Then TRIS-A equal to 0x01, which means I am going to use RA0 AN0 pin as an input pin. So to configure it as input, we specify it as 1, or to connect it as an output, we specify it as 0. So here we are connecting the potentiometer to AN0 pin, so we have used 1. Then in port B and port C, I have connected LEDs, which are output devices. So port B and port C are configured as output pins by putting TRIS-B equal to 0x00, TRIS-C equal to 0x00. Then I am going to set the ADCON value 0 to be 0x05. Now let us go and see. ADCON 0. So here I have set it as 05. So 0, 0, 0, 0, 0, 1, 0, 1. So this is 0, this is 5. So ADCON 0 is set with 0x05, which means ADC S1, S2, I am setting it as 00, which is nothing but F oscillator by 2, which is the clock frequency. So we have connected a 10 megahertz clock. So 10 megahertz, it is internally divided by 4, so it becomes 2.5 megahertz. So the 2.5 megahertz is again divided by 2, so it becomes 1.25 megahertz. So that is the conversion clock period. Then CHS2, CHS1, CHS0 is configured as 000, which means we have selected channel 0, which is nothing but RA0 AN0 pin. And then I am setting the value of go bit to be 1. Then I say start the conversion process. So once the conversion is complete, the ADC will change this bit 0, 1, 2, second bit. It will be changed from 1 to 0. Thereby it indicates the conversion is complete. Then we are switching on the ADC. So this is the configuration part. So we are starting the conversion process and check whether this bit goes to 0 or not. So that is what we do in our 0x05 set to a ADCON 0 value. Then in a while loop, I am going to check the second bit of ADCON 0. So second bit of ADCON 0 is nothing but go done bit. If that go done bit goes to 0, which means conversion is complete, then I need to read the result. So I read the result from two registers, ADRESL and ADRESH, and this result goes to port B and port C. So in order to visualize the result, I give a delay of 1 second. Then I am again going to switch on the ADC. So by F2 equal to 1, which means we are going to start the conversion again. So after starting the conversion, since it is in a while loop, again I am going to check whether the go done bit goes to 0. If it goes to 0, which means conversion is complete, read the result from ADRESL and ADRESH. Send the value to your port B and port C, which is connected to the LEDs. So after doing this program, let us build this program, convert this program into hexadecimal file. Now let us go and import this hexadecimal file onto the Proteus environment. So right click on the IC, edit properties, select the program file. Micro C, LED underscore ADC, and the processor clock frequency is 10 megahertz. Press OK. Now we have imported the hexadecimal file onto the microcontroller. Now let us check how the microcontroller is going to perform. When I use the play button, you can see Right now it is 0, remaining all are 1, which means it is at 2.5 volt. So this is the value for your 2.5 volt. So which means the half the value. So entire range is 5 volt. So now the needle is at the center. So it is 2.5 volt. So if I want, I can reduce the voltage. You can see when I change the reference or the input voltage to the ADC, you can see the corresponding binary bit pattern changes. Same way I can increase the voltage. Thereby you can visualize the change in the binary bit pattern. If it goes to a maximum value, then we will get all ones. Okay, so all ones as an output. So 5 volt, it is given by 10 ones. Same way 0 volt will be given by zeros. You can visualize the result. When it goes to 0 volt, you can see all are 0. So thereby changing the potentiometer value, I can change the output from your ADC. So here in this program, we have seen how to connect a potentiometer to a PIC16F877 and how to visualize the result on a LED. So in the next program, we will try to see how to interface a temperature sensor LM35 to a PIC microcontroller and try to visualize the result in a LCD display. So thereby, if the room temperature is 30 degrees will be shown on the LCD display. So let us start a new program. In this program, we are going to interface LM35 temperature sensor to the channel 0 of PIC16F877 microcontroller. So here I have shown a LM35 temperature sensor which has 3 pins, where the pin number 1 is a supply pin which can be connected with voltage from 4 to 30 volt, and pin number 3 will be ground, and the pin number 2 will produce an analog voltage corresponding to the temperature value. So this LM35 will give a resolution of about 10 millivolt per degree centigrade. So for example, if the room temperature is 30 degrees, then the LM35 will give 300 millivolt as a result through pin number 2. So for every degree, 10 millivolt variation will be there. If the room temperature is 30 degrees, then 30 into 10 millivolt, which is nothing but 300 millivolt, will be obtained as an output. So this LM35, it can work from minus 55 degrees centigrade to 150 degrees centigrade. So it gives an accuracy of about 0.5 degrees centigrade, and its operating voltage is from 4 to 30 volt. So we'll be connecting this LM35 temperature sensor to channel 0 of your PIC16F877 microcontroller. Then we connect a 16x2 LCD in a 4-bit mode to the port D. So here port D4, D5, D6, D7 is connected to D4 to D7 pins of LCD, and port D3 pin is connected to enable pin of LCD. Port D2 pin is connected to RS, register select pin of LCD. So this is the block diagram representation of interfacing a temperature sensor with PIC16F877 microcontroller. Now let us go to Proteus environment and build the circuit. Create a new project. Select a location for your project. ADC, LCD. Select a name for the project. ADC, LCD. So select a location for the project, select a name for the project, press next. I'm going to use a default schematic, press next. I'm not going to create any PCB layout, so I'm going to leave it as it is. No firmware is selected. Press next, only schematic is selected. Press finish. So first we will pick all the components. Pick PIC16F877, add it to the list, LCD. I'm going to select a 16x2 LCD. Here you can see the 16x2 LCD. Add it to the list. Then we require crystal, capacitor, switch, resistor, and LM35. So here you can see a LM35 sensor. It has 3 pins. Pin number 1 is VCC pin. Pin number 3 is ground, and pin number 2 is the output voltage corresponding to the temperature. So add it to the list. So these are some of the components required. Press OK. So now let us, after selecting the components, let us start building the circuit. So first let me select the IC, put it onto the circuit. Then crystal, place it onto the circuit. Connect it to pin number 13 and pin number 14 of your IC. Connect the capacitors to the crystal. Other end of the capacitor, I am going to connect it to the ground. Terminals mode, ground. Select the value for the capacitor, 33 picofarad. Select a value for the crystal. I am going to use 10 megahertz crystal. Select 10 megahertz. So this completes the oscillator circuit part. Next, we need to build the reset circuit. Select a switch, resistor, connect one end of the resistor to the switch, other end connect it to a supply. Connect the other end of the switch to a ground. And the intermediate point, I am going to connect it to the memory clear pin. So by default, this memory clear pin will be at logic high. Whenever I close the switch, the memory clear pin will go to logic low, thereby reset operation will be carried out. Now let us interface the LM35. Go to components mode, select LM35, place it onto the circuit, connect this pin number 2 to channel 0 of your microcontroller. And other end, pin number 1, I need to connect a supply. Pin number 3, I will connect it to a ground. So this connects the LM35 to your microcontroller. Now let us connect the LCD to your microcontroller. Go to components mode, select the LCD, place it onto your circuit. So here D4 will be connected to D4 of your LCD, D5 to D5, D6 to D6, D7 to D7. Then enable line, I am going to connect it to D3. RS line, I am going to connect it to D2. So other lines, I am going to connect it to ground. Place it onto your circuit. Connect D0 to D3 to ground. Same way RW bar, also I am going to connect it to ground, because from microcontroller always a write operation is going to be carried out. We are not going to do read operation, so I am going to connect this RW bar to the ground. Then VEE is for contrast adjustment. Usually it will be connected to a potentiometer. So here I am going to connect this VEE to a ground, which means I am going to have a high contrast of the LCD. Then VSS, again it's a ground line. I need to connect it to ground. Then VDD is a supply line, which I need to connect it to a power supply. So select the power, place it onto your circuit, connect it to your VDD. So this completes the circuit part. So where we have put the oscillator circuit in place, reset circuit, LM35 and LCD is also connected to the microcontroller. Now let us save the circuit and let us go and build the embedded C program. So let us open micro C, create a new project. So select a location for your project. So I am going to give a name, LCD underscore ADC. So select the microcontroller for which the programming is going to be done, and the device clock frequency I am going to set it as 10 MHz. So 4 things we are doing: selecting a location for the project, give a name for the project, select the microcontroller and the oscillator frequency. Press next, press finish. So here we are going to put our code. So let us save this file with the name LCD underscore ADC. Save. Let me copy the program. So here I have written the program. So copy this program, paste it onto this editor window. So now let us discuss this program. So we have connected RS, LCD RS is connected to D2, enable is connected to D3, LCD D4 is connected to port D4, D5 is connected to port D5, D6 is connected to D6, and D7 is connected to D7. This gives the connection, how the LCD and microcontroller are connected. And this specifies the direction of your port lines. D2 to D7 is configured as a output port lines. So that is given by this configuration here. Now let us initialize few variables. Since our result will be a 10-bit result, I want to store this 10-bit result. So I declare a ADC underscore read variable with a data type of unsigned integer. Then I use 2 character arrays, text and text1, to put some string onto it and then use the string to display it on the LCD. Then in order to save the string value of the temperature, I use a character array which I can store 5 elements there. Then another variable long temp is also initialized. So when we start the main program, I try to disable all the interrupts by putting intcon. Intcon is an interrupt control register. If I put it to 0, which means all the interrupts will be disabled. We are not going to use any interrupts. So intcon is set with 0. Since port D is connected to LCD, which is an output device, so I say tris D equal to 0x00, which means port D is configured as an output pins. Then addcon 1, I am going to set it as 0x00, which means 80 represents ADFM bit will be 1, which means result will be stored on the right side, and PCFG3 to PCFG0 is set to 0000, which means all the port A pins are configured as analog pins. Then tris A is set with 0xFF, which means port A is configured as an input port. Then I use LCD initialization to initialize the LCD. Then send some commands like cursor is off, clear the buffer register before displaying any content. Then I initialize two arrays, text equal to LM35 temperature. Text 1 is initialized with sensor interface. Then I use a command LCD underscore out 1 comma 1, which means first row, first position, LM35 hyphen temperature will be displayed. So this function LCD underscore out is an auto increment function. When we put L in 1 comma 1, then automatically the subsequent position will be enabled. 1 comma 2, M will be displayed. 1 comma 3, 3 will be displayed. 1 comma 4, 5 will be displayed. So like that, it is in an auto increment mode. So the address of each position of character will be automatically incremented, and thereby the characters will get displayed. So then in the second row, first position, I am going to put sensor interface. In order to see this value, I am going to use a delay function of 2 seconds. So for 2 seconds, LM35 temperature and sensor interface will be visualized. Then in a while loop, we read the channel 0 using ADC underscore read. So ADC underscore read is a library function available in your ADC library. In micro E libraries, you can see system libraries. I have a ADC library. So in ADC library, we have this ADC underscore read function is available, which is used to read a particular channel. And the corresponding converted result will go to your ADC underscore read. So a 10-bit value will come to your ADC underscore read. So we are going to use that. So let me enable this ADC library. Then this 10-bit value needs to be converted into a voltage. So for converting it into a voltage, we multiply this ADC underscore read with 4.88, where this 4.88 is the resolution of your ADC. So if I use a reference voltage of 5 volt, since it is a 10-bit ADC, we get 5 volt divided by 2 power 10 minus 1, which is nothing but 4.88 millivolt. So the 10-bit value is multiplied with the resolution of your ADC to get the actual voltage. We already know that the temperature sensor gives 10 millivolt for every degree centigrade. So in order to convert the voltage into a temperature, we divide this value by 10. So if the room temperature is 30 degrees, the voltage will be 300 millivolt. So I need to convert this 300 millivolt to 30 degrees. So thereby I divide it by 10. So thereby 300 millivolt will become 30 degrees. So now I have a binary value representation in temp. So this should be converted into a string. Then only it can be displayed in your LCD. So in order to convert the integer value to string, I use a function integer to string, which is available in the conversion library. In conversion library, you can see there is a integer to string function here. So I am going to make use of this integer to string function to convert your integer value to a string. So the string will be placed onto the array temperature. So I am going to clear all the values in the buffer register. Then in 1 comma 1, first row, first position, I am going to put the temperature. In second row, first position, I am going to put in centigrade equal to, then I put the temperature content. Whatever we have measured, that string content, we are going to place it next in the second row. So it will be displayed for 2 seconds. Again, the channel 0 will be read, converted into a voltage value, converted into a temperature value, then convert that value to a string, display it on the LCD. So this process continues again and again. Now let us build the circuit. So in order for this LCD functions to operate, so let me select the conversion library as well as the LCD library. So LCD library is also enabled. Now let me build the circuit. So it got converted properly. Now let us go and import this hexadecimal file onto our microcontroller. Right click on a microcontroller, edit properties, select the program file. LCD underscore ADC, open. Select the processor clock frequency, which is 10 megahertz. Press OK. So now we have imported the hexadecimal file onto the microcontroller. Now let us see the logic. You can see temperature sensor interface. Then it shows temperature equal to in centigrade 27. So right now the LM35 measures 27 degrees. So it is showing 27 here. So when I start increasing the temperature, you have the arrow here. So I can start increasing the temperature values. You can visualize the output displayed here also gets changed. Now 30 degrees. So it shows 30. So I can increase and you can visualize the change in the output value. Similarly, you can also decrease the value. So thereby your displayed value also gets modified. You can see right now the 27 degrees is set. So the LCD is also displaying 27 degrees. So this is how a temperature sensor can be interfaced with your PIC16F877 and the values can be monitored using a LCD. So in this tutorial, I have discussed about on how to interface a temperature sensor with PIC16F877. So first we started with any sensor can produce a voltage. So that voltage is mimicked with the help of a potentiometer. So I connected a potentiometer to a PIC16F877 and tried to visualize the result in a LEDs. And in this program, second program, we discussed about on how to interface a temperature sensor LM35 with PIC16F877 and the result is being visualized in the LCD. Thanks for watching. Please subscribe for more technical learning. Thank you.